Hey guys, in this video I'm going to talk about the center of mass, which is covered in 8.6 and 8.7 in the text. Try to clarify some issues in there because it's a pretty simple chapter, but the book is a little bit confusing in some places, so I hope to clear that up. And also, really conceptually, the content of 8.6 and 8.7 is very important because it's the reason why we think the free body diagrams we've been using this entire semester make sense at all. So I hope to clarify that for you, both conceptually and provide some mathematical foundation for it. So first, to illustrate why we even need to care about the center of mass, consider trying to slide a car on ice. So here's my car, and we've mostly been considering forces like the following. I push on the car slides, no problem. Well, what if I consider something slightly different? I want to push the car, but I want to push it off center, something like over here. Well, if you weren't in this class, your logical intuition of the situation would say that the car would spin, because obviously you're pushing off center, you're on ice, there's no friction, so the car would just start spiraling. But you're in physics, and so you know that that force is going to make the car translate in the horizontal direction. So actually, from physics this semester, you think that the car moves in a straight line. So what's the problem here? Obviously, we can't have both of these things be the right answer, and we think that physics is going to describe the real world in some limit, so what does this mean? Well, actually what we've been doing in this class is we've been having an implicit assumption that forces only act at the center of mass. So we have not really been considering the idea of having a force acting offset to the center of mass. We've been assuming that all forces act at the center of mass. So we should be asking ourselves, does this matter? And we have a short answer and a long answer, and the short answer is no, but also the long answer is yes. So what I mean by this is it doesn't invalidate anything we've been doing before because we've been using this assumption, but actually we should start to consider forces that act off the center of mass. So first let me explain why this doesn't invalidate anything we've done before, up to this point in the class. Alright, so here's figure 8.13 in the text, and it shows this exact phenomenon I'm talking about. Two particles, the center of mass is denoted with a red X, and the force we're applying is denoted with a blue arrow. So you can see here, we act with the force off the center of mass, and the system starts to spin. Here's the force acting on the other side, system starts to spin. Here's the force acting at the center of mass, system just translates. And of course, this is the situation we've been assuming for this entire class. Well, in fact, you can see that the motion of the center of mass, the red X, is exactly the same in all these three cases. It just happens that the mass in this case goes a little bit further than the mass it does down here, but the position of the center of mass is the same. So in fact, we find that we've just been blindly writing Newton's second law, but actually what we meant was that the forces can be acting pretty much anywhere we like, but what we get out of it is the motion of the center of mass. So we have been assuming that this is the situation we've been considering, but actually it doesn't matter because the center of mass motion is the same no matter where the force acts, even if it acts off the center of mass. So it doesn't matter means that we get the right answer for the motion of the center of mass. Everything we've been doing up to this point in the class describes the motion of objects as a whole, meaning the whole thing is translating described by the motion of the center of mass. When I say it does matter, meaning that we actually are not getting all the information by considering that the forces were acting at the center of mass, we actually do need to consider this, that essentially means that we can't describe anything but the motion of the center of mass. So up to this point in the class, we can't describe these kinds of motions. We can't describe the motion of the car spinning on the ice. We know that happens, but we can't do it. So this is the first step we're going to take into being able to describe that kind of motion by describing what the center of mass is and what it really means by applying forces in various places. So the rest of this video is going to talk a little bit about what the center of mass is, how motion about the center of mass works, and then later we're going to talk about how rotational motion works, and this is going to be the content of chapter 10, which we'll cover in a couple of weeks. So the first thing we want to do is we want to find the center of mass for some simple system. So let's find the center of mass of this rod with three masses on it. Well, essentially the center of mass is some kind of average position. It's the place where if you held onto the object, it would balance. It wouldn't move in the gravitational field. So it's some kind of average of the masses on the object, and I'll just give you the definition. It is the mass of 1 times the position of 1 plus the mass of 2 times the position of 2 plus the mass of 3 times the position of 3 divided by the total mass. So that's what I mean by an average. It's the positions weighted by the size of each mass divided by the total mass. So this represents some kind of weighted average, weighted by the masses that are on the bar. So that's the case of all the masses being in one dimension. We can obviously consider a two-dimensional case or a multi-dimensional case. So think of these three masses being anywhere in space. Say like that. I need to define a coordinate system, of course. Put my coordinate system right there, and I need to describe the position of these masses, so I'll put some vectors on here for that. There we go. R1, R2, and R3 are the position vectors of the masses, and so the center of mass is pretty obvious. You just need to keep the masses in this expression the same, and then upgrade the positions to vectors. There we go. So this is the full definition of the center of mass in the multidimensional case, because we got vectors everywhere. So of course I've been doing this with three definite masses. You could have any number of masses. This would just be a sum over, M4, R4, M5, R5, whatever, and then you would put the sum of all the masses on the bottom. And of course you can do this not with just discrete objects, but with a continuous set of masses. That requires calculus. So you take each mass, which is some finite value, you make it an infinitesimal, so make it a tiny little mass, and then you take a limit. So what this is going to look like, something like the following. So the center of mass is going to be, we're going to take a limit of some expression. Here's the expression we want to take the limit of. I've just replaced each mass with an infinitesimal mass, but the position vectors are still the same because each one of those infinitesimal masses are at some position. And then when you do this limit, this just turns it into an integral of RdM. So this is the definition of the center of mass for a continuous set of masses. M here is just the sum of all the masses. Doesn't need to be inside the integral because no matter how we take this limit, this mass is always going to be the same. You don't need to integrate over all the masses, just like you didn't need to put the position here. This was just a sum of all the masses. This thing is just all the masses. So this is the integral form. We may be using this at some point during the semester, but for us this is going to be the slightly more important way to think about the center of mass, the average position of the masses. Okay, so now we're ready to think about the motion of objects as a whole instead of the motion of just their center of mass. So I'm going to start with the center of mass equation here for some I objects. So there could be some large number of objects in this system. If I wanted to find the velocity of the center of mass of the system rather than the position, which is what I give here, I can just use the definition of velocity. Of course, that's the time derivative of the position. So if I do that into this equation, I want to take the time derivative of this. The masses are not changing in time, so by taking the time derivative of this, I'm going to end up just taking a time derivative of the individual positions of each object in the system. And that's going to look something like that. So this is almost the exact same expression as with the center of mass equation, except that now this is something like the center of the velocity, but we call it the velocity of the center of mass. So I can continue to play this game and try to find the acceleration of the center of mass. That's the derivative of the velocity with respect to time, and the derivative carries through in the same way, so we just get derivatives of the velocity of each individual object, which looks like that. So now we have some accelerations. Of course, we know that the accelerations are related to the force, so I want to start talking about the forces on this object because I want to relate it back to the free body diagram. And I'm just going to do a quick rewriting where I've just replaced the sum of all the masses here with the total mass. I'm going to do some algebra to move the total mass over to the center of mass side of the equation. But now look at this. This looks like some kind of statement of Newton's second law. We have a mass times the acceleration over here. We have a sum of all the masses times the acceleration of each object over here. So let's try to rewrite this using Newton's second law. So this is the total mass times the acceleration of the center of mass. So that's something like the net force on the center of mass, which I'm going to write like that. And on this side, we have the sum over all the mass times acceleration of each object. So this is going to be the net force on each object in the system, and then we're going to sum over all of those net forces. So I'm going to write that like this. And so we can use this to sort of see why our free body diagram model for objects kind of works. So what I'm going to do is I'm going to take an object in the gravitational field, and I'm going to model it as a bunch of particles. Alright, so here's my penguin, which I'm going to use to describe this. So I'm going to break this penguin into 3 different points. Okay, so these 3 points represent, something like the penguin's head, then something like the penguin's body, and then something like the penguin's tail. The penguin has a total mass m, then each one of the points has a mass m over 3. I've just collected all of the mass into 3 equal parts. So these masses are obviously attracting each other because the penguin is staying as a whole penguin. There's some kind of interaction, some kind of penguin interaction that's happening between these points. So I'm going to put forces in to represent that interaction. Okay, so those are the internal interactions of the penguin molecules. And I'll also put in the gravitational force because, of course, this is a massive penguin and the gravity is going to act on anything massive. And the gravitational force on each one of the masses is going to be m over 3 times g, because each one is a third as big. So now I want to somehow turn this picture, where I've broken up the penguin's mass into these 3 individual masses, into a picture which includes just the mass of the center of mass, just the free body diagram. So I should use this equation. I want to take all the net forces acting on each object and add them together. This object has 2 forces, this has 3, this has 2, so I'm going to add these 2 together, add 3, add these 2. But because these guys are Newton's third law pairs, they are going to cancel. So all the internal forces are going to cancel, and all you're going to be left with are the 3 external forces. So the sum over all the forces on the center of mass is going to be equal to just those 3 forces, and that's exactly the same thing as you would get if you just had a single penguin mass. So let me draw that. There's our single penguin mass, which is about 3 times as big as those, and now I'm going to draw the gravitational force, where I have just added them head to tail. That gives a total gravitational force like that, which is obviously going to be m times g, because each one of these is m over 3 times g. So, the takeaway here is that all the internal forces canceled, and so all we had left were the external forces, and that gave me my sum of all the forces acting on the center of mass. So, by putting all the forces in the first place on the center of mass in my free body diagram, I didn't lose anything. I get exactly the same amount of information because all these guys are connected. Now, the case with some force which is not acting on the center of mass, which is what we're going to start considering pretty soon, that's the case where we have some other external force on the penguin, say somebody's pushing on the penguin like that. Then this particle will have another external force. If I do the sum here, I'll end up with 1 force left over, and that is not acting on the center of mass. You can see that it's acting on the one up here, and so we'll need to consider extended bodies and extended diagrams to be able to fully incorporate the motion of these more complex objects. Okay, great. I hope this video was clarifying and told you a little bit more about where we're going to go in this class as well as where we are right now. Okay, thank you guys.